All right, everybody. So we're getting towards the end of Unit 4, right? We're wrapping up. We kind of are piecing everything together. We just had our Part 1 test on all the nomenclature stuff, and we're wrapping up all of our structure stuff. So Vesper theory, polarity, coming back into organic, the structure of organic molecules, functional groups, but really, what the functional groups do to the polarity of the molecule and what types of intermolecular forces they have. And then we are kind of wrapping it up at the end is like, why do we care about the types of IMFs different compounds have? What does that tell us about the compound? What can we predict if we know the polarity of a molecule or the types of IMFs that it has? What are we going to do with that information? So we're finishing up Unit 4, and we're kind of trying to put everything together in terms of polarity, solubility, intermolecular forces, boiling points, all that stuff. So this lesson is going to just try to take you through all that stuff and then kind of tie in the functional groups that we've been learning in organic chemistry and how they fit into that puzzle. All right, so let's just go through this outline here. All right. So again, what we're going to kind of put all together are these concepts. Boiling points of different compounds. Why, different compounds have different boiling points. Intermolecular forces, solubility, and polarity. All right. So let's go into it. All right. So how do polarity and solubility connect? Okay. So sometimes you're asked, would this compound be considered water soluble? So what we're asking is if something's water soluble, that means it mixes well with water, it's miscible. And if something's not soluble in water or insoluble in water, it's not miscible, right? So think of the things that might mix with water. We know ionic compounds like salt dissolves in water, it mixes well with water, but oil doesn't, right? They don't mix together in a homogeneous solution, right? They make a heterogeneous solution. But salt and water make a homogeneous solution. So salt is soluble in water, but oil is not, right? And the question is why, all right? So there's a simple rule to follow, and it's a little bit more complicated than this rule, but especially at this level of chemistry, it's okay to follow this rule. It's like dissolves like. All right, and so what we mean by that is polar compounds mix with other polar compounds, and nonpolar compounds will mix with other nonpolar compounds. So these two will mix together. Polar dissolves in polar, and nonpolar dissolves in nonpolar, but they don't mix together. So polar and nonpolar don't mix. All right, so if you reframe the question, right? So when we're asked if something is water soluble, we're really being asked, is this polar or nonpolar? If it's polar, then we would expect it to be water soluble, and if it's non-polar, it wouldn't be expected to be water soluble because we know water's polar, right? All right. Since we know water is polar, something is soluble in water when it is also polar, right? Like dissolves like. Polar mixes with polar. Okay. So since we know water is polar, stuff that mixes with water should also be polar if we follow our rule. Right? Like dissolves like. So again, if you're asked if something's water soluble, that's another way to just say, hey, is this a polar molecule or a nonpolar molecule? Is this a polar substance or a nonpolar substance? But then also another thing to think about is if you know something does mix well with water, if you know something is water soluble, then you know that thing probably is polar. Okay? So if you're told ammonia mixes well with water, well, that means ammonia is probably polar. And it is. We already know that ammonia is polar. But if you're told X is water soluble, X is probably polar. And if you're told that Y is insoluble in water, then Y is probably nonpolar, right? So something is insoluble in water when it is nonpolar, okay? So it doesn't mix well if it's nonpolar, doesn't mix well with water if it's nonpolar, and it will mix well with water if it is polar, like dissolves like. So ammonia, NH3, mixes well with water. Why? Well, H2O is polar. We know that. And NH3 is polar, right? This is bend-shaped, asymmetrical polar. This is trigonal pyramidal, which is asymmetrical. It is also polar. And if you really want to get into the true rule of like dissolves like, yeah, you can just keep it as polar and non-polar mixes with non-polar if you want to. But the more alike the intermolecular forces are, the more or the better they'll mix together. So the more soluble they'll be, the better they'll mix together. So why is ammonia really soluble? Because not only is ammonia polar, like water is polar, but they both have hydrogen bonding intermolecular force, right? So their strongest IMF is hydrogen bonding. So because they're both polar and they have hydrogen bonding, they're going to be very soluble, okay? But again, solubility, to make it simple, is just like dissolves like, okay? So oils don't mix well with water, right? We already know that, right? That must mean oils are non-polar. Oh, there you go. Now, what are oils? Well, we should kind of know this already. Fossil fuels, oil, gases, gasoline, octane, that kind of thing. And now we can, since we've been learning organic chemistry, naming, methane, propane, octane, right? These are all hydrocarbons, and hydrocarbons are non-polar. They have to be non-polar because they don't have polar bonds. Remember, the carbon-carbon bonds in a hydrocarbon are obviously non-polar because there's zero electronegativity difference. And remember, we say the carbon-hydrogen bond is non-polar. So if all you have is carbon and hydrogen, and that's all hydrocarbons have, is carbon and hydrogens bonded to each other, there are no polar bonds, so it really doesn't matter what the shape of the molecule is. If you don't have any polar bonds, the molecules can't be polar. So hydrocarbons, okay, fossil fuels are non-polar, and they don't mix well with water, okay? So what do hydrocarbons mix well with? Well, water is a common solvent, but what dissolves in water? We know polar things dissolve in water, and salts, right? And a way to think about salt, why is salt soluble in water? Why are ionic compounds generally soluble in water? Why do they mix well? Well, you can think of an ionic compound as 100% polar, right? Sodium chloride, you have a positive one side and a negative one side. So think, it's not like, we don't say ionic bonds are 100% polar, but it's a good way to think about it. So they're very polar, so that's what makes them water soluble, right? So what about nonpolar things? What would they mix well with? Well, they would have to mix well with nonpolar solvents. So a common nonpolar solvent is benzene, which is C6H6. It's a common organic solvent for nonpolar things. All right, so all benzene is a hydrocarbon, so it's nonpolar, and so other things that are nonpolar would dissolve in benzene, right? So benzene's a nonpolar solvent, and it will mix well with nonpolar things, and water is a very common polar solvent, and it will mix well with polar things. All right. Okay, so again, if you're asked about solubility, it's like dissolves like. If you're asked what will dissolve in water, polar things should dissolve in water because water's polar. Now what will dissolve in benzene. You know that benzene, C6H6, is nonpolar, so that would be nonpolar things. And then if you have a polar thing and a nonpolar thing, they won't mix well together. Okay? Now there's always exceptions to the rule, but that's the general rule that we kind of follow. All right? And it'll lead you down the right path most of the time. All right. So when something, now we're going to tie in intermolecular forces and boiling points, okay? So when something vaporizes, when something boils, right? So what we're saying is, if we're thinking about water vaporizing, it goes from liquid to gas, okay? Understand what's being broken. What has to happen? The water molecules have to move fast enough that the water molecules separate from each other. Well, what's holding water molecules together? They're hydrogen bonding, they're intermolecular forces. So when something vaporizes, it's not the bonds inside the molecule that break, it's the bonds between the molecules. And I shouldn't use the word bonds there, it's the intermolecular forces between molecules. And in water's case, that would be the hydrogen bonding has to break, right? So if you have to break intermolecular forces in order to vaporize a compound. What would determine how fast the particles have to move? So what we're really saying is, what would determine, like, why would something have a high boiling point? Why would the molecules have to move really fast to overcome their intermolecular forces? Well, it must mean they have strong IMFs. So boiling point is completely dependent on the strength of IMFs. But let's understand what we're doing here. So understand, when H2O liquid goes to H2O gas, we're not breaking the individual water molecules apart. That bond stays intact, right? Those bonds stay intact. What are we breaking from the liquid state to the gas state? We're breaking those intermolecular attractions. So remember, this would illustrate as hydrogen bonding between water molecules, right? So that's what has to break. And so if these attractions are really strong, these particles must move really fast to break them. Well, speed of particle is really, directly proportional to the temperature of the particle. So if you have strong IMFs, they're not going to break unless you get to a high temperature, okay? So again, IMFs are broken when something vaporizes, not actual bonds. We're not breaking any covalent bonds when water vaporizes. If sodium chloride melts and then vaporizes, we're not breaking bonds. We're breaking IMFs, right? So hydrogen bonds are broken, okay, not the covalent bonds. So what determines the boiling point of a substance? And it would also be true about the melting point. What determines the melting point of the substance? It's the strengths of the IMFs. It's the strengths of the IMFs. The stronger the IMFs, the higher the boiling point. The weaker the IMFs, the lower the boiling point, right? And, if you look at, I think water and CO2 are really good examples to look at, because they both have 3 atoms, right? You got 1 carbon and 2 oxygens in CO2, and you got 2 hydrogens and 1 oxygen in water, okay? And water is bent, and it makes it polar, whereas CO2 is linear, and it's symmetrical, so it's non-polar. And CO2 has more electrons. It's a bigger molecule than water, so it has greater London dispersion than water, okay? But CO2 is a gas at this temperature. In fact, CO2 sublimes into the gas state at negative 78 degrees Celsius. So CO2 has really weak IMFs compared to water. And the reason that is because water is polar and it has its hydrogen bonding, whereas CO2 is symmetrical and nonpolar and only has London dispersion. It has greater London dispersion than water does because it has more electrons and it's a bigger molecule than water. But that hydrogen bond is so much stronger that water has, and CO2 just can't keep up with it. So if water weren't polar, it would be a gas at this temperature, right? We wouldn't be having this conversation if water weren't polar, because if it weren't polar, it would have very weak London dispersion forces, and it would vaporize, we're talking probably negative hundreds degrees Celsius, okay? So stronger IMFs means higher boiling points. So why does H2O have a higher boiling point than propane, right? Propane, we use that in our gas grill. It's a gas right now. Water is a liquid, right? So all the propane at this temperature is vaporized, but the water is still a liquid. That must mean water has stronger IMFs, okay? It has a higher boiling point, so it has stronger IMFs. Well, if we look at the two, right, water has hydrogen bonding and London dispersion forces because it's polar, okay? But this is just a hydrocarbon. Propane is just a hydrocarbon, so the only IMF it has is London dispersion. So because water has stronger IMFs, we should expect it to have a higher boiling point, okay? So water's hydrogen bonding is what makes it have a much higher boiling point than other gases that might even be bigger molecules, right? It's those hydrogen bonds that hold those water molecules together, and they have to be moving really fast. So be at a higher temperature to break those interactions, okay? So let's do this. What if we were told to rank the following compounds from highest boiling point to lowest boiling point, all right? So we got ethane, we got HCl, we got methane, CH4, and we got water, okay? So if you're asked to rank from highest boiling point to lowest boiling point, what we're really asking you to rank is strongest IMFs to weakest IMFs. Strongest IMFs would have the highest boiling point, weakest IMFs would have the lowest boiling point. That's what we're really asking, okay? And so what we would do is say, okay, well, water's polar and it has one of our special bonds, so its dipole-dipole interactions are really hydrogen bonding. So water has hydrogen bonding in London dispersions. HCl is polar, so it has dipole-dipole interactions in London dispersion forces. Ethane is just a hydrocarbon, so it only has London dispersion forces. And methane is a hydrocarbon, so it's nonpolar, so it only has London dispersion. So the expected outcome would be water would have the highest boiling point because it has the strongest IMFs listed, and ethane and methane would have the weakest or the lowest boiling point. Now, how do you distinguish between the ethane and the methane? Well, when you're only comparing London dispersion, remember it's about total number of electrons in the molecule and also the size of the molecule. So ethane is just a bigger molecule with more electrons than methane. So we would expect the London dispersions in this molecule to be stronger than the London dispersions in that, okay? All right, so what if you have 3 different substances at the same temperature, okay? And you know their states of matter. So here's 3 different substances. I2, iodine, and it's a solid at room temperature. Water, we know, is a liquid at room temperature, and propane is a gas, all right? Well, here's the deal. Let's not even look at the actual IMFs in each thing. Let's just understand what that tells us, solid, liquid, gas, all right? If you have things at the same temperature, all of the solids have stronger IMFs than the liquids, and all of the liquids have stronger IMFs than the gases. So in the room with you right now, if you look around, the solids have the strongest IMFs because in the liquid, any liquid, if you have some water with you, it has the second strongest IMFs. And all the gases in the room, the air you're breathing, all those particles have the weakest IMFs. Because at the same temperature, there was enough energy to vaporize all the gases, but there wasn't enough energy to melt any of the solids, right? So just by looking at this, I know that iodine, I2, must have stronger intermolecular forces than water, and water must have stronger IMFs than propane, okay? Now, some of you might be saying, well, wait a minute, iodine's nonpolar. So it only has London dispersion forces, kind of like propane. Propane's nonpolar with London dispersion only. Iodine is nonpolar with London dispersion only. And water is sitting there with hydrogen bonding, the strongest of them all, right? Well, remember, all right, you can't just blindly say hydrogen bonding is always stronger than London dispersion, okay? When things are similar in size, hydrogen bonding is going to beat London dispersion. Similar in size, similar in number of electrons. But if we look at iodine, iodine has 106 electrons. 53 plus 53. Water only has 10 electrons. So water has hydrogen bonding, but unfortunately, it's not strong enough to overcome the 106 electrons, the big electron cloud of iodine and its random London dispersion forces, okay? So if I asked you what has a higher boiling point, iodine or water, and I didn't remind you that iodine was a solid, then I would expect a lot of you to say water has a higher boiling point or a higher melting point than iodine because it has hydrogen bonding and all iodine has is London dispersion. So, and I would accept that answer if I didn't remind you that iodine was solid. But if you know iodine's a solid at the same temperature water's a liquid, that's a way to tell you, that is a way to tell you that iodine's IMFs are stronger than water's IMFs. So it just must mean that iodine's London dispersion is stronger than the combined IMFs of water, okay? So this solid and liquid is telling you that this is stronger than that, right? If I just said I2, but I didn't tell you the state of matter, and I said H2O, now I expect you to know that water is a liquid at room temperature. You should know that. But, and we did our periodic table unit, and you should know iodine's a solid, but I probably wouldn't hold you responsible for that. So if I just blindly said iodine without telling you the state of matter and water, again, an acceptable argument would be like, oh, well, because water's polar and it has hydrogen bonding, it's going to have a higher boiling point than iodine. Okay, but the right answer, the true answer is, wait a minute, nope. The London dispersion in iodine is so much stronger than the combined hydrogen bonding and London dispersion in water, and it's just because it has so many more electrons, right? Okay. So how can we bring in organic with it? Well, okay, so let's bring in our functional groups. So you want to go back and review your functional groups and know, remember, if you have a functional group, now without a functional group, you just have a hydrocarbon, and hydrocarbons are nonpolar, so just London dispersion. If I add a functional group, now the molecule is polar. And the question is it polar and can have hydrogen bonding, or is it polar and just has dipole-dipole interactions, right? So let's rank these organic compounds in order of increasing boiling point. So we have to remember, if it ends in -one, this is propanone, that means it's a ketone. It has a double bond O, all right? If it ends in ane, ene, or ine, then it's just a hydrocarbon, so just London dispersion forces. And remember, if it ends in OL, that's an alcohol. That means it has an OH group, all right? So we need to know that alcohols can have hydrogen bonding, whereas ketones and aldehydes with just the double bond O have dipole-dipole interactions. And then if it's just a hydrocarbon, just London dispersion. So increasing boiling point, the propane would have the weakest or lowest boiling point because all it has is London dispersion forces. Then followed by the ketone because it has dipole-dipole interactions as well as London dispersion forces. And then would be the alcohol because the alcohol has hydrogen bonding in London dispersion forces. Okay? And just by looking at the name, I know hydrocarbon, or not even just the name, just looking at the suffix. Ane, hydrocarbon. Ene, hydrocarbon. Ine, hydrocarbon. Boom. Just London dispersion. One, or al, one, ketone aldehyde. Dipole-dipole. Ol, hydrogen bonding. Okay? Alcohol, hydrogen bonding. Okay? So make sure you review your prefixes, know which ones are, have that fond bond, H bonded to F, H bonded to O, or H bonded to N. So the H, you're really, for functional groups, you're looking for the H bonded to O, and you have H bonded to O in alcohol groups and acid groups, carboxylic acid groups. So alcohols and carboxylic acids and amines, remember amines have an NH bond. So you have a fond bond. So amines, carboxylic acids, and alcohols can hydrogen bond, but ketones and aldehydes and ethers and esters just have dipole-dipole interactions. Okay? And then if it's just a hydrocarbon, just London dispersion. Okay? All right, so hopefully that kind of ties things together and you can do all your practice stuff. And don't be surprised, the Unit 4 test part 2 will probably be coming out in about a week. The announcement will be in Schoology, all right?